Look inside a modern personal computer, and nearly everything that gives it power is concealed. The processor rests beneath a metal heat spreader, memory dies hide inside black packages, and controllers for graphics, storage, networking, and communication spread across the motherboard like cities too small for the naked eye to see. A single chip may contain billions of transistors, yet the complete machine can sit quietly on a desk. That feels ordinary now because modern life has been built around microelectronics. In the middle of the 20th century, however, the idea of creating many electronic components together inside one tiny piece of material seemed almost impossible. Computers were assembled one part at a time. Every transistor, resistor, capacitor, diode, connector, and length of wire had to be manufactured, positioned, joined, and tested. As engineers demanded more power, the machines grew larger, costlier, hotter, and increasingly difficult to keep working. Two men, working independently at rival American companies, found different paths through that barrier. Jack Kilby at Texas Instruments built the first working integrated circuit. Robert Noyce at Fairchild Semiconductor developed a silicon design far better suited to reliable mass production. Behind Noyce's solution stood Gene Hoerni, whose planar process provided the manufacturing foundation on which modern chips would be built. So who truly invented the integrated circuit? History does not offer an honest one-name answer. Kilby proved that integration could work. Noyce showed how it could become a practical industrial technology. Hoerni created the process that allowed the concept to scale. Their contributions were distinct, yet together they changed electronics and made the personal computer possible. To understand the scale of their achievement, imagine building a computer before the microchip. Early electronic systems relied heavily on vacuum tubes. A tube could amplify or switch an electrical signal, but it was bulky, consumed substantial power, generated intense heat, and eventually burned out. A sophisticated machine might require thousands of them, filling rooms with cabinets, cooling equipment, thick cables, and maintenance crews searching for the component that had failed. The transistor, demonstrated at Bell Laboratories in 1947, transformed this world. It performed many of the same functions while occupying far less space and using much less energy. Yet the transistor did not solve the entire problem. It was still a separate physical object, just like every resistor that limited current, every capacitor that stored charge, and every wire that carried a signal between one device and the next. As designers attempted to build more advanced radar systems, communication equipment, guidance computers, and business machines, the component count climbed relentlessly. Each new part had to be fabricated, measured, mounted, soldered, inspected, and connected. Every junction became a potential failure point. A circuit might be flawless on paper and still collapse because a wire broke, a solder joint cracked, a connector corroded, or one component was installed incorrectly. Shrinking the individual pieces helped, but it did not remove the growing forest of connections. Engineers called this crisis the tyranny of numbers. The phrase captured a troubling truth. A machine could become so complicated that assembling it reliably was almost impossible, even when each individual part was reasonably dependable. In a system containing tens of thousands of components, small failure probabilities multiplied. Wiring consumed space, assembly costs rose, heat accumulated, and vibration weakened mechanical joints. Military designers needed greater computing power inside aircraft and missiles, where every kilogram and every cubic inch mattered. Computer manufacturers wanted more memory and logic, but customers could not afford endless rows of hand-wired cabinets. Electronics required more than smaller transistors. It needed a fundamentally different method of construction. A useful analogy is a city in which every building is constructed separately and every road is added afterward by hand. Making the buildings smaller only delays the crisis, because the road network becomes ever more tangled. The real breakthrough would be to create the buildings and the roads together as parts of one planned structure. In electronics, that meant forming active devices, passive elements, and eventually their interconnections inside a single body of material. The dream existed before Kilby and Noyce. In 1952, British electronics specialist Geoffrey Dummer publicly described the possibility of building electronic functions within a solid block of semiconductor material, eliminating the conventional web of separately connected components. Dummer had worked with radar and understood how size and reliability limited complex systems. He recognized the direction in which electronics needed to move, but he could not produce a practical commercial device. Electronic functions within a solid block of semiconductor material, eliminating the conventional web of separately connected components. Dummer had worked with radar and understood how size and reliability limited complex systems. He recognized the direction in which electronics needed to move, but he could not produce a practical commercial device. His experience illustrates a pattern that appears throughout technological history. One person may describe what ought to be possible, another may prove the principle in a laboratory. Others must invent manufacturing processes, testing systems, packaging methods, and business models capable of turning the idea into something repeatable. Dummer helped identify the destination, but the road remained unfinished. By the late 1950s, many engineers understood that integration was necessary. What they lacked was a reliable way to create several useful circuit elements within one semiconductor body, connect them, and make the result survive outside an experimental laboratory. Jack St. Clair Kilby entered the story not as a celebrity, but as a quiet, practical engineer who understood the frustrations of miniaturization. In 1958, he joined Texas Instruments in Dallas, an important semiconductor company searching for ways to build smaller electronic systems. One proposed approach used miniature modules, very small individual parts assembled into compact packages. Kilby saw that this still avoided the central difficulty. In 1958, he joined Texas Instruments in Dallas, an important semiconductor company searching for ways to build smaller electronic systems. One proposed approach used miniature modules, very small individual parts assembled into compact packages. Kilby saw that this still avoided the central difficulty. Tiny, separate components remained separate, and every one of them still needed a connection. Soon after he arrived, an unusual circumstance gave him time to think. As a new employee, he had not earned vacation leave when much of the company departed for its summer holiday. The laboratory became quiet. Desks stood empty, meetings paused, and the usual interruptions disappeared. Kilby turned his attention to the materials themselves. Transistors were already made from semiconductors. Resistors and capacitors were normally treated as different categories of components. Yet, semiconductor material could also be shaped to perform those functions. If the essential elements of a circuit could all be formed from the same substance, perhaps they no longer had to be manufactured as separate objects. They might be created together within one piece of semiconductor. In his notebook, Kilby sketched a circuit in which the necessary elements shared a single body of material. The idea did not instantly produce a finished product, but it broke through a conceptual wall. The answer to the tyranny of numbers might not be a cleverer way to assemble thousands of parts. They might be created together within one piece of semiconductor. In his notebook, Kilby sketched a circuit in which the necessary elements shared a single body of material. The idea did not instantly produce a finished product, but it broke through a conceptual wall. The answer to the tyranny of numbers might not be a clever way to assemble thousands of parts. It might be the removal of that assembly step altogether. Texas Instruments allowed Kilby to test the idea. The prototype he built looked nothing like a modern processor, used germanium rather than the silicon that would later dominate the industry. The device was narrow, delicate, and surrounded by fine wires. Its electronic elements were formed within one semiconductor body, but their electrical connections were still made with tiny external conductors. To modernize, it appears crude, yet appearance was not the point. The device was narrow, delicate, and surrounded by fine wires. Its electronic elements were formed within one semiconductor body, but their electrical connections were still made with tiny external conductors. To modernize, it appears crude, yet appearance was not the point. Kilby was not attempting to create a finished mass-market chip in a single leap. He wanted to answer a more fundamental question. Could different circuit elements formed in one semiconductor structure operate together as a complete electronic system? On September 12, 1958, he demonstrated the device to managers at Texas Instruments. He connected it to test equipment, applied power, and watched a waveform appear on an oscilloscope. The signal was simple, but its meaning was profound. The circuit worked. Kilby had built and demonstrated the first functioning integrated circuit. On September 12, 1958, he demonstrated the device to managers at Texas Instruments. He connected it to test equipment, applied power, and watched a waveform appear on an oscilloscope. The signal was simple, but its meaning was profound. The circuit worked. Kilby had built and demonstrated the first functioning integrated circuit. Active and passive elements could be formed together and made to operate as one system. For the first time, integration was no longer only a proposal or an elegant drawing. It was physical reality. At the same moment, the prototype revealed what remained unresolved. The external wires were difficult to attach and unsuitable for circuits of great complexity. Germanium would not become the preferred material for large-scale chip production. The device could not yet be reproduced economically by the thousands or millions. Kilby had opened a doorway, but beyond it lay a narrow, fragile path. The integrated circuit still needed a structure that allowed both the components and their connections to be manufactured together across a flat semiconductor surface. While Kilby was proving the principle in Texas, a different engineering culture was taking shape in California. Robert Noyce was a physicist, inventor, and unusually gifted leader who could connect technical insight with commercial opportunity. In 1957, he and 7 colleagues left the laboratory of transistor pioneer William Shockley. Shockley angrily referred to them as the traitorous 8. But their departure became one of the defining events in the birth of Silicon Valley. With backing from Fairchild Camera and Instrument, they founded Fairchild Semiconductor. The new company was not simply a research laboratory. It aimed to manufacture dependable silicon transistors and sell them into demanding markets. Silicon offered important advantages, yet early silicon devices suffered from serious surface problems. Contamination and electrical instability at the exposed surface could damage performance, shorten life, and reduce manufacturing yield. Jean Hoerni, a Swiss physicist and one of Fairchild's founders, developed a powerful solution known as the planar process. In this method, the silicon wafer was covered with a protective layer of silicon dioxide. Engineers opened carefully selected windows in that layer, introduced impurities into the silicon beneath, and created regions with precise electrical behavior. The oxide protected the surface, improved reliability, and produced a flat structure that could be processed photographically. Hoerni had done more than make a better transistor. He had established a manufacturing platform. Noyce recognized the larger possibility hidden inside Hoerni's process. Silicon dioxide is an electrical insulator. If a thin metal layer were deposited on top of it, that metal could carry signals across the chip without interfering with the silicon below, except where deliberately opened contact points connected the two. Noyce proposed forming several components in one silicon body, protecting them beneath oxide, opening contacts where necessary, and depositing aluminum across the surface to create the interconnections. Instead of attaching microscopic wires one at a time, the conductive paths could be patterned during manufacturing. Components and connections would emerge from the same sequence of controlled steps. This was the decisive difference between Kilby's first working circuit and Noyce's practical architecture. Kilby had proved that integration was possible, but his device still depended on external wiring. Noyce made the wiring part of the chip. His approach used silicon, a material particularly suited to the planar process because it naturally formed a useful oxide. The design could be repeated across a wafer, allowing many circuits to be manufactured simultaneously. It offered a path toward greater complexity, smaller dimensions, improved reliability, and high-volume production. Noyce was not merely copying Kilby's idea in another material. He reached an independent solution from the perspective of manufacturing. Kilby had asked whether a complete circuit could exist within one semiconductor structure. Noyce asked how such a circuit could be connected, protected, and reproduced without hand-installed wiring. Ideas alone still had to become hardware. At Fairchild, Jay Last led the team that turned Noyce's concept and Hoerni's process into working planar integrated circuits. Engineers created masks, controlled diffusion steps, deposited metal, defined patterns with light, tested wafers, cut them into individual chips, and protected the finished devices inside packages. Nothing about this early production was automatic. Yields were low. Dust particles ruined circuits. Imperfect masks distorted features. Diffusion steps produced the wrong electrical characteristics. A design could be theoretically correct and still fail because one tiny contamination particle entered the process. The modern semiconductor industry emerged from thousands of such manufacturing details being understood, measured, and controlled. The process also changed the economics of invention. A complex circuit no longer had to be assembled as a unique object by a technician at a workbench. Once engineers had created the photographic masks and stabilized each production step, the same pattern could be repeated across an entire wafer. Dozens of circuits could be exposed, treated, connected, and tested together. A successful design, therefore, became more valuable with every improvement in yield, because the knowledge invested in one pattern could produce a growing number of identical devices. This repeatability separated the integrated circuit from many earlier forms of miniaturization and allowed electronics to advance through generations rather than isolated masterpieces. At the same time, the companies moved toward a legal confrontation. Texas Instruments filed Kilby's patent application for miniaturized electronic circuits in February 1959. His claim focused on creating multiple circuit elements within one body of semiconductor material. Later that year, Noyce filed an application describing a semiconductor device and lead structure with practical on-chip interconnections. The historical importance of their claims overlapped, but their technical emphasis differed. Kilby could point to the earlier working demonstration and the concept of a complete circuit formed from one material. Noyce could point to a silicon planar structure with integrated metal connections that made large-scale manufacturing realistic. The patent dispute continued for years because the commercial stakes grew with every improvement in chip technology. If integrated circuits became the foundation of electronics, control of the key patents could influence entire industries. Courts and patent offices examined questions of priority, scope, and technical distinction, yet progress in the laboratory moved faster than the legal debate. Companies needed access to crucial methods, and the expanding semiconductor market could not remain frozen while lawyers searched for a single perfect verdict. Texas Instruments and Fairchild ultimately entered licensing arrangements. The legal system recognized important elements of both positions, and history retained both names. Kilby and Noyce came to be regarded as co-inventors because each contributed something indispensable. Kilby delivered the working proof. Noyce provided the practical monolithic silicon architecture. At first, however, many engineers remained skeptical of integrated circuits. Discrete components were familiar and visible. A technician could measure one transistor, replace a resistor, inspect a solder joint, or choose a capacitor with a particular value. An integrated circuit sealed several elements inside a single package. If one internal part failed, the entire chip might be discarded. Early devices were also expensive because manufacturing yields were poor. Many circuits on a wafer did not function. For simple products, separately packaged transistors sometimes appeared cheaper and easier to trust. The advantage of integration became undeniable as electronic systems grew more complex. Once a production process had been established, one wafer could carry many identical circuits. Their connections were created by patterned manufacturing rather than attached by hand. Components sat extremely close together, allowing signals to travel rapidly. Fewer external joints improved reliability, and the same design could be reproduced again and again. Manufacturers steadily improved wafer purity, photolithography, oxide quality, diffusion, metal deposition, packaging, and testing. More chips worked, the cost per circuit fell, and a powerful economic cycle began. Higher production volumes paid for better equipment. Better equipment improved yield. Higher yield reduced prices. Lower prices attracted new customers, which pushed volume still higher. The first buyers willing to pay the premium were often military and aerospace organizations. In those fields, small size, low weight, reduced power consumption, and reliability were not conveniences. They could decide whether a mission succeeded. Guidance systems required considerable electronic capability inside missiles. Aircraft and spacecraft, where every gram and every connection mattered. Texas Instruments and Fairchild supplied integrated circuits for these demanding applications, and government contracts forced the young industry to improve quality and consistency. The Apollo program became one of the best-known early users. The Apollo guidance computer performed navigation and control tasks inside both the command module and the lunar module, relying on integrated circuit logic when the technology was still young and costly. Large orders did not magically perfect chip manufacturing, but they created sustained demand for reliable devices and supported production on a scale that helped lower costs. Engineers developed rigorous tests, traced failure mechanisms, standardized procedures, and learned how to build circuits capable of surviving vibration, temperature changes, and the harsh conditions of spaceflight. Every improvement made integrated electronics more attractive for commercial systems. Chips soon entered industrial controls, communication equipment, medical devices, calculators, and computers. The earliest devices contained only a handful of transistors and performed limited logic functions, yet the underlying method could scale. If a few components could be integrated, designers could aim for dozens, then hundreds, thousands, millions, and eventually billions. Manufacturing features became smaller, new circuit families appeared, memory chips stored greater amounts of information, and logic devices replaced boards once crowded with discrete transistors. Electronic systems shrank, even as their capabilities expanded. Kilby continued exploring products made possible by integration. At Texas Instruments, he contributed to work that led toward compact electronic calculators. A machine that once required bulky mechanical assemblies or desk-sized electronics could eventually be carried in one hand. The calculator offered ordinary users a clear demonstration of what integrated circuits could accomplish, a familiar function, dramatically reduced in size and cost. Decades later, Kilby received many honors, including a share of the 2000 Nobel Prize in Physics for his role in the invention. The Nobel Committee deliberately honored him for his part in the achievement, language that recognized both the importance of his work and the broader collaborative history. Noyce's career followed a path that shaped Silicon Valley itself. Known not only as an inventor, but also as a leader who favored a less rigid corporate culture, he left Fairchild with Gordon Moore in 1968 to establish Intel. The new company first concentrated heavily on semiconductor memory and later became central to the development of the microprocessor. Placing the major processing functions of a computer on one chip depended entirely on the integrated circuit tradition created by Kilby, Noyce, Hoerni, and the engineers who transformed their concepts into repeatable production. The road from the first integrated circuit to the personal computer was neither short nor direct, and neither Kilby nor Noyce invented the PC. Their contribution was more fundamental. They changed the way complex electronics could be constructed. Before integration, additional computing power generally required more separate components, more boards, and more connections. Afterward, increasing amounts of logic could be placed inside standardized chips. Computers did not shrink merely because engineers made their cabinets slightly smaller. Entire sections of circuitry vanished into silicon. The transformation unfolded in stages. Small-scale integration placed a few logic gates on one chip. Medium-scale integration combined larger functional blocks. Large-scale integration raised transistor counts further. Semiconductor memory replaced many bulky technologies used for active data. In 1971, Intel introduced the 404, widely recognized as the first commercially available general-purpose microprocessor on a single chip. It contained roughly 2,300 transistors, a minuscule number by current standards, but a remarkable achievement at the time. Later processors handled wider data paths, executed more instructions, and addressed larger amounts of memory. Hobbyists began building microcomputers, companies introduced machines designed for desks, and the personal computer industry emerged. Every major PC component depended on integrated electronics. The central processor was a chip. RAM modules carried integrated memory devices, disk controllers, graphics adapters, network interfaces, sound cards, keyboard controllers, and motherboard chipsets all relied on semiconductor circuits. Even power supplies eventually incorporated sophisticated control chips. As integration advanced, functions once provided by separate expansion cards moved onto the motherboard and later into the processor package itself. Modern systems on a chip can combine processor cores, graphics, memory control, security, and communication in one compact device. The extraordinary achievement is not simply that chips became smaller, they also became more reliable and far less expensive for each function they perform. A modern processor may contain billions of transistors and require an astonishingly complex manufacturing process, yet identical units can be produced in enormous quantities. That is the mature expression of Noyce's manufacturing vision. At the same time, every one of those transistors participates in a circuit that depends on the principle Kilby proved. Multiple electronic elements can be formed and operated together inside one integrated semiconductor structure. John Hoerni's contribution is often obscured when the story is reduced to a contest between Kilby and Noyce. That simplification distorts the history. Noyce's manufacturable solution relied on Hoerni's planar process. The protective silicon dioxide layer made stable, flat devices possible, and supplied the insulating surface on which metal connections could be patterned. J. Last and his colleagues then converted those ideas into working Fairchild products. Production engineers refined each step. Chemists improved the materials. Equipment designers built machines capable of precise alignment. Test engineers learned to identify microscopic defects. Packaging specialists protected fragile chips while providing reliable connections to the outside world. The integrated circuit was an identifiable invention, but the semiconductor industry was a collective construction. Jeffrey Dummer also deserves a place in that lineage because he publicly described the solid circuit direction before anyone produced a working example. His failure to manufacture one does not erase the value of his insight. Instead, it reminds us that invention takes several forms. One person may see the destination, another proves it can be reached, a third builds a practical road, while countless others create the tools, factories, standards, and industries that make the journey routine. So who really invented the integrated circuit? Jack Kilby deserves recognition for building and demonstrating the first working device in 1958. His germanium prototype proved that circuit elements formed within one semiconductor body could operate together. Robert Noyce deserves equal recognition for independently conceiving a silicon monolithic circuit based on planar manufacturing and on-chip metal interconnections. His structure supplied the practical foundation for scalable production. John Hoerni must be credited for the planar process that made Noyce's approach possible. Kilby and Noyce are therefore properly described as co-inventors, not because their work was identical, but because it was complementary. Kilby showed that the electronic city could exist on one piece of land. Noyce demonstrated how its roads could be created across the surface during construction. Hoerni prepared the stable ground and protective layer that made the city reliable. Without Kilby's demonstration, integration might have remained an uncertain theory for longer. Without Noyce's interconnection method, it might have remained too awkward to manufacture at scale. Without Hoerni's process, silicon technology would have lacked the platform on which complexity could grow. Their story teaches that being first is not the same as being complete. Kilby produced the first working integrated circuit, yet his prototype was not the form that eventually dominated the market. Noyce's design more closely resembled the structure of modern chips, but it followed Kilby's physical proof and depended on Hoerni's earlier manufacturing breakthrough. Patent law attempted to separate their claims. History ultimately joined them. Modern electronics carries all three contributions. The personal computer on a desk today stands decades beyond Kilby's fragile device. Its processor may perform billions of operations each second, its memory can hold billions of bytes, and its graphics hardware can generate entire simulated worlds. Yet the conceptual leap behind those capabilities occurred when engineers stopped treating every electronic function as a separate physical object and began constructing circuits as unified structures. Imagine attempting to assemble a modern processor from billions of individually packaged transistors, each connected by hand. The result would be physically impossible, economically absurd, and almost certain to fail. Integration is not merely one feature inside a computer. It is the condition that allows a modern computer to exist. The same principle extends far beyond personal computing. Integrated circuits control automobiles, aircraft, medical scanners, hearing aids, cameras, household appliances, industrial robots, satellites, communication networks, and phones. They calculate, remember, regulate, measure, display, and communicate, usually without being noticed. Their success has made them nearly invisible. People see a device's screen, case, buttons, and software, but rarely consider the microscopic layers of semiconductor, oxide, and metal hidden inside. The chip disappeared into the objects it transformed. It became less a single product than a universal method of construction. Kilby died in 2005 after witnessing the integrated circuit reshape society. Noyce died in 1990, before the Nobel Prize recognized Kilby's contribution and before mobile computing and the internet reached their present scale. Because Nobel Prizes are not awarded posthumously, Noyce could not share the 2000 award. That fact sometimes leads people to assume that history recognizes Kilby alone. Yet major scientific and technological institutions continue to identify both men as central inventors. Noyce's influence also lived through the companies and culture he helped create. Fairchild trained engineers who went on to establish many semiconductor businesses. Intel became one of the defining companies of the personal computer age. The surrounding region became known as Silicon Valley, a name that reflects the material at the heart of Noyce and Hoerni's work. Kilby's legacy endured in the proof that a complete, useful circuit could be integrated. His quiet summer at Texas Instruments showed that the tyranny of numbers could be defeated not by managing an ever-growing web of connections, but by eliminating most of those connections at the source. The near-empty laboratory, the fragile germanium bar, and the waveform on the oscilloscope marked the opening of a new industrial era. Return now to the modern computer from the beginning of this story. It starts, loads an operating system, opens applications, connects to networks, edits video, processes sound, and responds instantly to human commands. None of these actions appears connected to a laboratory demonstration in 1958 or a Fairchild design conceived the following year. Yet every instruction travels through integrated circuits descended from those breakthroughs. The next time you see a processor, only a few centimeters across, imagine the alternative world the microchip prevented. Computers occupying entire buildings, wires filling endless cabinets, technicians constantly searching for failed joints, and advanced electronics available only to governments and the largest corporations. Personal computing required many inventions, including the transistor, semiconductor memory, the microprocessor, magnetic and solid-state storage, displays, operating systems, and software. Beneath all of them, however, stood the integrated circuit. It allowed electronic complexity to rise, while size, energy use, and cost could fall. The question of who invented it remains compelling because people naturally search for one hero and one decisive moment. The real history is richer. Jeffrey Dahmer saw the direction. Jack Kilby proved the principle. Gene Hoerni established the planar foundation. Robert Noyce designed the practical interconnected silicon structure. Jay Last's team built early Fairchild devices, and thousands of engineers turned fragile experiments into a global industry. No single contribution makes the others unnecessary. One person opened the doorway, another built the road, and another prepared the ground. The world moved forward because their achievements connected. Inside every modern computer, the answer to the tyranny of numbers is repeated billions of times. Transistors no longer stand alone across large circuit boards. They live in microscopic communities, linked by metal pathways, patterned with extraordinary precision. The integrated circuit did more than reduce the size of computers. It expanded what humanity could afford to imagine, manufacture, and carry. That is why Jack Kilby and Robert Noyce both belong at the beginning of the microchip age. Kilby's first working circuit and Noyce's manufacturable silicon design were not rival endings. They were two necessary beginnings, strengthened by Jean Hoerni's planar process and by the engineers who transformed invention into production. Together, they gave the modern world its hidden electronic foundation. The personal computer became possible when the circuit stopped being a hand-assembled collection of separate parts and became one manufactured whole. From that tiny whole grew an industry powerful enough to place the capabilities of once unimaginable machines on desks, in pockets, inside vehicles, throughout hospitals, and eventually almost everywhere.